Okay, okay, let's get started. So, uh, in the previous class, we learned about how to handle a hazard. So we learned about the data hazard detection, and then also we learned about the control hazard, how to handle the control hazard. So actually, in the data hazard, if the data hazard is detected, then the pipelines cannot be propagated to the next stage. So, so we need to detect the data hazard, and then the following instruction is stored. It's a it's stored in the ID stage, right? That's how to handle data hazard. Also, in the control hazard, the control hazard is caused by taken branch, right? So actually, for the normal case, so it means for normal instructions, the next instruction will be executed one by one, right? So which means, so we can just add the PC by 4, right? Because the size of a single instruction is 4 byte. But when the branch is taken, so if uh, the current instruction is the branch instruction, and then the branch is taken, then that means program counter, the PC value is changed to the some target, right? Target of the branch instruction. But the problem is that the branch is the result of the branch is determined late, right? So that was the problems, the performance issues by the control hazard, right? So you can just understand the why performance can be degraded by the taken branch instructions. And then I explained because the branch is determined, the result of a branch is decided late, right? Then what is the solution? Solution is, so we can, if we can detect the result of a branch instruction earlier, then we can reduce the wasted cycles, right? So that's how to handle the control hazard. So, but I explained that the solution in the textbook, so will cause the another data hazard. So I don't. So that's why I don't like this solution, right? So I explained this solution. So we can have the dedicated branch instruction, branch unit, okay, branch unit, and so we can handle we can detect the result of a branch instruction earlier because so because the ALU needs to handle the various operations. So that means the ALU is more complex. But for branch instruction, we can just subtract. We can just perform subtraction, right? So it means if we have the dedicated branch unit, unit, then we can reduce the delay of the branch instruction. Actually, the delay for subtraction, right? But even though we use this solution, but the two cycles will be wasted by taken branch. So, so in the CPU, we have a branch predictor. Okay, so so this is the first prediction technology. So you will learn in this course. Actually, our CPUs include the many prediction technologies. Actually, this is very critical to the performance of the CPU, right? So actually, our CPUs employ many prediction technologies, right? And then actually, these technologies are called speculation. Uh, as It's called the speculation. Okay, but the meaning is prediction, right? Actually, the speculate to represent some. Yeah, in Korean, it can be translated into 투기, like the uh, 부동산 투기 or some other the 주식 투기 or some, something like that. But in so it means actually the meaning of speculation is a little bit stronger than the prediction, right? So so for example, so why do we uh, invest our money to the some some buildings or apartment in Korea? In Korea, it's kind of apartment 투기 because we assume that the price of apartment will increase continuously, right? So it means we just think that the hit rate, the prediction will be correct with higher probability. We assume, right? We we just so based on the history, so based on the some previous events, we can expect that the correction rate, it is called hit rate. So if our prediction is correct, then it's called a hit. Hit, it's a hit, HIT. So if we know the hit rate is very high, then we can just apply our prediction. So which means we can predict the future event, and then based on our prediction, so we can execute this future event, right? So this technique is actually widely used in our CPU. Okay, so the branch prediction is called the dynamic branch prediction. So dynamic prediction is one of speculative technology, speculation, right? So so it means actually the prediction rate, the prediction hit rate is very, very high. It's around 97 to 99% hit rate. Okay. So it means we can just execute our CPU based on our prediction result because the hit rate is extremely high, right? Then what is the benefit of a prediction in branch? We can just predict the result of a branch instruction. So which means we can, it's a prediction, just a prediction. So we can predict the result of a branch instruction earlier, right? It means we can reduce the number of wasted cycles by taken branch. So branch prediction means that we can just predict the taken or not taken events of the target branch instruction. And then I mentioned that, so we can just predict the result of a branch prediction by monitoring previous events, the previous result of branch instruction. So this is the example. So actually in the previous class, my pen did not work well. so, so this is the iterative loop. So, and then actually if we use the for I go 0 and then I is less than 100 and I plus plus, what happened? I plus plus. Then we already know that this iterative loop will repeatedly execute the statement inside of the loop, right? And then I mentioned that usually the branch instruction is in the last line of the statement. So if this is, then it jumped to the first line of this loop. Okay, so you can know that this is the taken branch, right? Obviously, it's taken. because it jumps to the the first line. So if it's not taken, then the next line, the next instruction will be executed, but it jumps to the first line of the loop. So it's taken branch, right? So, and then if we do not apply the branch prediction technology, then for this taken branch, for every taken branch, the two cycles will be wasted, right? So, so it means if this loop is repeated 100 times, then 200 cycles will be wasted, right? So so let us assume that there is only one instruction here. Then in order to repeat this one instruction, 200 cycles will be wasted, right? It's very huge actually. So we can apply the branch prediction. So, and then as I mentioned, in order to apply the branch prediction, we need to monitor the previous events of this branch. Okay. So one bit branch prediction means that we monitor the only one event, one previous event of the target branch instruction. I mentioned the target branch instructions. So it is because our code will include many branch instructions, right? And then we can monitor the behavior of individual branch instructions, right? Because the behavior is different for different branch instructions, right? Right? Then how can we identify different branch instructions? So for example, this is the BQ1, BQ2, and then BNE, and then blah, blah, blah. So there can be many branch instructions in our code. And we need to identify different branch instructions. How? So for example, there are many variables like A, B, C, D in our code, or in our C code, right? And then how can you identify these different variables? So we give different names, the variable names, but actually how in the CPU, how can we identify different variables? Address, right? Because so I mentioned that if we declare new variables, then the CPU assign this variable in the memory. So in the different memory space, right? And then we can identify different memory space using different address, right? Like address B, so address C. So actually, even though we just name the variables using the alphabet, right? Like English letters, but actually in a CPU can identify different variables using addresses, right? Then how about the different branch instruction? So different instruction. We can use address also because so I mentioned that the instructions are also stored in memory, right? And then in order to identify different instructions, we can use addresses of these instructions. Then what does that mean? PC, program counter. So using program counter, we can identify different branch instructions, like different instructions. Then how? So we know the PC of this branch instruction, BQ1. Then we just store the previous event, like the previous event of this branch instruction in the memory, but this is the buffer, not real memory. So this is some dedicated memory for branch prediction. Okay, so we can just store the previous event in the buffer. So this is some different type of memory or dedicated memory in CPU, right? So we store this buffer, and then the address of this entry will be the PC of this PQ, right? Then if this PQ is executed again, then using this PC, then we can access the previous event, right? Then we can get the result of a previous event of this branch instruction. Then by checking this, we can know the previous event, and then based on this previous event, then we can just decide the predicted result of this branch instruction. Okay, so actually the branch predictor is buffer, is a buffer, and then the address of the entry of this buffer is accessed by PC, the PC of the branch instruction, right? Then we can get the result. Also, we can update the event of the branch instruction in this buffer. Okay, so the branch predictor is also called BPB. So it means branch prediction buffer. So it is because the events of this branch is stored in the buffer. Okay. So, and then we can access this buffer using the program counter of the branch instruction. Okay. So, but for this nested loop, so we can also frequently use the nested loops in our code, right? So like the for I equals 0 and then blah, 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 for j equals 0 and then blah, blah, blah. So we frequently use nested loop for in our code. But what is the problem of one-bit branch predictor? It is because the inner loop. So actually, for the inner loop, then when the at the end of the inner loop, then and then at the so the for the one iteration of this outer loop, we just repeated this inner loop, right? So it looks like the taken, not taken, and then taken, not taken. Okay, so this is the behavior of the inner loop, right? So what's the problem? So we mispredict. So this is the miss. So if the prediction result is incorrect, then it is called a miss. It's a miss. Miss. Then also the next event is miss with the one bit predictor because it's not taken. So we can just expect that, oh, next event is the also not taken. Okay. So it is mispredicted at the end of the loop also for the first loop because the inner loop will be repeated again. So, and then it's mispredicted again. So this is some kind of the disadvantage of one bit branch predictor. So we can use the 2-bit branch predictor. So actually, so I posted the homework, and then you can also find the question about that is 1-bit and then 2-bit branch predictors. Okay, so 2-bit branch predictor. The 2-bit branch predictor uses 2 bits for monitoring past events. And then this 2-bit works like the saturated counter. So what does it mean? For each branch instruction, then it just used the counter like 002, 1, but this is the saturated counter. And then if the branch is taken, then the next count value becomes the 0, 1. And then it's taken, then it becomes 1, 0, and it's taken 1, 1. And then it's taken again and again, but it's saturated. So 1, 1 again. It's not taken, then the value is decreased by 1. So it becomes for this state, and then if the branch is not taken, it becomes 1, 0, 0, 1, 1, 0, 0. And then we just predict that if the discounter value is 0, 0, or 0, 1, then we predict that the branch will not be taken. Okay, it's a not taken. It's predicted as the not taken. And if this counter value is 1, 0, or 1, 1, we predict that branch will be taken. So this is the 2-bit branch predictor. Okay, then what's the benefit? what's the benefit of this branch predictor, 2-bit branch predictor? So it just give some higher priority if the branch is taken many times. What does that mean? For example, for this example, the inner loop, the behavior of inner loop will be taken, 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 not taken, 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 blah, blah, blah. Okay? It looks like this. Then, if we use the 2-bit branch predictor, then the state will be 1, 1 for this case. Okay? Then we just predict that, oh, it's taken, right? But it's mispredicted. Okay? So it goes to the 1, 0, right? Because the discount value is 1, 0, then for the next event, we just predict that this branch will be taken. So this is hit. Then it becomes the count value becomes the 1, 1. And then taken, 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 again, again, again. So hit, 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 hit. So compared to the 1-bit predictor, right? So for the 1-bit predictor, actually for this inner loop, then it mispredict at the end of the loop and then at the beginning of the loop, twice. But if we use the 2-bit predictor, then it just mispredicted at the end of the loop or the inner loop, right? And then it's hit at the beginning of the loop. Okay. So you may think that it's just one case, right? So we just reduce the one misprediction in this branch predictor, right? But in order to implement this, then the branch predictor size needs to be increased because for each branch instruction, we need to store 2 bits like 0, 0, 0, 0, or 1, 1, 0 like this. Okay. But actually, so as I mentioned, the performance of branch prediction is critical to the performance of our CPU. And then actually, in the commodity CPU, it's the popular CPUs like by Intel or AMD or also Apple. So commodity CPUs include very complex branch predictors. Okay, and then so actually the researchers still work on these branch predictors. It is because we need to increase the hit rate of the branch predictor to increase the performance of a CPU. And then actually in the CPU, it's very critical for the performance of CPU actually. Okay, so you may think that actually the 1% of performance improvement, so you may think that this is very small, but actually in Intel and the CPU vendors, 1% of performance improvement is very critical. Okay, so and then also I also worked in the Intel, and then I heard that, so if you can improve the performance of CPU 1%, then you can become some uh, part leader, like the Imon in Korea, so leader, okay, in Intel, right? Just 1% of the performance improvement, right? So actually, it's very critical. Okay, so so you may think that, so the that's why so we are applying the very complex techniques such as the data boarding, hazard detection, and then also the branch prediction, also like control hazard detection. Okay, so it's very critical. So and then also our CPUs use very complex structures, not like this. So we are learning about the five-stage pipeline architecture, but actually our CPUs include very complex architectures. It's a very different actually. So and then the performance of CPU is also can be improved by some different techniques, right? So these techniques are also very critical for the performance of CPU. Okay. So so in a homework, so I also uh, added some question that include that handles the branch predictor. So actually you can compare the performance of a 1-bit and 2-bit predictor in the question. Okay. Okay. So using the branch predictor, we can predict the result of a branch instruction. But in order to perform the branch instruction, then the another another thing is required. What's that? So the result of branch instruction, the result of branch. So actually, branch updates the PC using the target of branch instruction based on the result, like taken or not taken. And then branch predictor just predicts this result, the taken or not taken. So and so it means in order to execute the branch instructions, actually you need to know the target of branch instruction. Then what is the target? So what does that mean? Actually, we also need to predict the target of branch instruction also. Then then we can just predict the, the execution or behavior of branch instruction. Okay, so we also store the target of branch instruction. Okay, like BQ, X1, X2, and target. And then we just calculate the target of a branch instruction, like the target PC of the branch plus target. Okay. So in order to execute the branch instruction, actually we can taken or not taken or not taken of the branch instruction, right? Uh, 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 uh. Okay, so we can just predict the result of a branch instruction, but how about the target? Actually, we need to know the target of the branch instruction in order to execute this branch instruction by prediction. Okay, but actually, we don't need to predict the target of the branch instruction. Why? It's constant value. So PC of the branch instruction is a constant because the PC is the constant value for each branch instruction. Also, how about the target? Target is the immediate value. So which means, immediate value is the constant value. So what does that mean? If if once we execute the branch instruction, so if we just execute branch instruction once, then we know the target of the branch instruction, right? So instead of calculating this target of the branch instruction, we just store the calculated target of the branch instruction in the buffer. Okay, so it's the buffer, and then we just the target of the branch instruction in the buffer, and then this buffer is also accessed by PC. Like the branch prediction buffer, we just in the branch prediction buffer, we just access the previous events of the branch instruction, and then we access the entry of this prediction buffer using PC. Target buffer is the same. We just store the target of branch instruction in the buffer, and then we access this target of the branch instructions using program counter of the branch instruction. Then, because this target is the constant value, then once this target is computed, then we can just store this target, and then we just use this target of the branch instruction. Okay. So if we do not store this target of the branch instruction, so then if we just use the branch prediction buffer, but we just have one cycle of a penalty, because in order to calculate the target of the branch instruction, then we need to fetch the instruction, right? Instruction from the instruction memory, right? We need to fetch branch instruction from instruction memory, then one cycle will be taken, right? But if we have branch target buffer, then we do not waste the cycle. So it looks like this. This is the instruction stage. Instruction fetch stage. And then, so using the PC, I explain here. So this is the instruction fetch and ID pipeline register. So it means this is the instruction fetch stage. So then this is the PC, and then using the PC, normally we access the instruction memory. Then we can get the instruction. Okay? And then using the same PC, we just access the branch prediction buffer. And we access the branch target buffer. So branch target buffer is also called BTB because branch target buffer, right? Then using PC, if the current instruction is the branch instruction, then we can get the result of branch instruction. Also, we can get the target of the branch instruction. Then, based on the result, if the predicted, this is the predicted result. Okay, predicted result. If the predicted result is taken, then using this target, we update the PC. Right? Then PC can be updated within instruction fetch stage. So what does that mean? If the is taken, so if this predicted result is correct, then the cycles will not be wasted by taken branch because we predict the result, and if this result is correct, we already know the target, and then usually the target is the constant value. The target is correct, usually correct. Okay, so and then the PC is updated within instruction fetch stage. So those cycles will be wasted. Okay, so actually, so in the modern CPU, the commodity CPU, instruction fetch stage is very complex because of this process. Like actually, the instruction needs to be fetched. Also, we need to have the branch prediction buffer or branch target buffer and branch target buffer. So actually, that's why the instruction fetch stage is actually very complex. The CPU. Okay, so I simplified the architecture of the instruction fetch stage. Okay, so by doing this, we can reduce the wasted cycles by control instructions, branch instructions. Okay, so so this is the branch prediction, branch predictor, and then so by doing this, we can reduce the control hazard. Okay, and now so this is the last topic in the process architecture exceptions. Okay, so we will learn how to handle exceptions in CPU in a CPU. And what is the exception? So as you can estimate, the exception means unexpected events in a CPU. So what does that mean? So for example, so like divide by 0, like A divided by 0. So CPU actually, the result is not defined, right? Actually, a certain number cannot be divided by 0, right? So actually, the Intel CPU, so if you compile the C and then if you just execute the this statement, then your binary code will be terminated. And then also you can find that exception. So exception is detected. And then the kind of exception is the divide by 0, right? Just like this. So exception is the unexpected event. So what does that, and it means it's not a normal event. So not the abnormal events can happen in a CPU, like the divide by 0. And then these events is to be also handled by hardware and operating system. Okay. So first, so I I mentioned that exceptions need to be handled by hardware and operating system. What does it mean? Hardware needs to firstly detect the exceptions, unexpected events in a CPU. And second, actually, it needs to report to the causes of exceptions. So that means the kinds of exceptions. And it needs to call exception handler. So in the operating system needs to provide the exception handler. So I said the operating system needs to provide exception handler. So which means actually the exception handlers are software. Okay, it's a software. Okay, the hardware just call exception handler. Okay, if the exception is detected, so these operations need to be supported by hardware. Okay, first detect, and then second, and report the causes of exceptions, and then call exception handler. Okay. So this is the undefined, so unexpected event. Also, some events are, so the CPU also needs to handle it's the expected event, but it's the rare events. It's a rare. Like, so, and then these events are called interrupts. So for example, so we can type the keyboard, right? And then if we type the keyboard, then computers need to handle this event, right? And then this type of events are called interrupts, right? And then also the interrupts are handled by operating system. It means software. Why? It's rare. It's an infrequent events. So even though we type our keyboard very quickly, very fast, but it's very slow compared to the CPU frequency, right? So the performance compared to the performance of CPU, our typing speed is very, very slow, right? So this event is handled by interrupt events, right? So interrupt is given, then also it works like this exception. First, interrupt is detected, then it calls the interrupt handler. Okay. So this event is given to the CPU using some hardware, because this keyboard is the hardware, right? And the event is also given to the CPU, and then CPU detects this event, and then this event is detected, and CPU calls the interrupt handler. Okay. So what does that mean? Our code, the CPU is running our code, right? The code, and then exception is detected or interrupt are detected. Like exceptions or interrupt are detected. Then CPU stores the current condition, right? And then it calls exception handler or interrupt handler. And then I mentioned that this is also software. And then exception handler or interrupt handler will be executed, and then it returns to our code. It's a return. So for this period, the exception or interrupt handlers are executed. So if you see this figure, then it's similar to function call, right? So it's similar to the jump instruction, actually. So I mentioned call exception handler, and then we also learned about the function calls, right? Call exception handler or function call. So actually, the exception handler is the operation of exception handler is similar to the function call. So we can just understand the exception handler like the function call, but it's the very special event, right? So unlike the function call, the CPU handles the exceptions or interrupt specifically, but the behavior is similar to the function call. So that's why the exception is also. So when I mentioned the control hazard, control hazard also includes the exceptions, right? Because the behavior of exception handling is similar to the function call, but it needs to be specially handled by CPU. Okay. And then so why do we handle why CPUs handle the exceptions in using software or software handler? Because these events are rare, right? So and then actually the hardware is a very precious resources, right? So how do we just implement the hardware to handle frequent events, right? Frequently handled event. But if some events are infrequent or very rare, then we can just handle these events using software. Because the software is very slow, right, compared to the hardware, right? But because these events are very rare, we can just handle this event using slow software, okay? So in order to support the exceptions, the RISC-V has some specific registers for the SCPC and then SCOSE. Okay. SCPC means the supervisor exception program counter. Okay, so supervisor exception program counter. It's called the SCPC. And then actually it is just save the PC of the offending or interrupted instructions. What does that mean? So for example, let us assume that divide by 0 is detected in CPU. And it means div instruction is executed in EX stage. Then And then I also explained that if the exception is detected, then our code is stopped, and then call exception handler. Okay, so which means it jumps to the PC of the exception handler, and then it returns, right? Return. Then what is required? Return address is required after the exception handler. So SCPC stores the PC of instruction that causes exceptions or interrupt. Okay, because we need to have return address after the exception handler. Understand? Do you understand? Also, I mentioned that a CPU is to report the causes of exceptions, and then these causes of exceptions are stored in the as cause. Okay, it's a supervisor exception cause register. Okay, and then so CPU first stores the PC of the offending or interrupted instruction, and then CPU stores the causes of exceptions, and then jumps to the exception handler. This is the operation, the required operations of exceptions. Okay. So, oops. Then also, then exception handler. So actually, as I mentioned, the exception handler is the software. Is right. So actually, the exception handler, the software code is executed, and if the restartable. So it means that if this exception is not critical, and it can be handled by software, then it returns to our code. Okay. So for example, we did not learn yet, like the page fault. Page fault is also a kind of exceptions. Okay, exceptions. And then this is actually if the page fault is detected, then the operating system handles the page fault and it returns to our code. Okay, so this is the restartable exceptions. Okay, then if the page fault is detected, then the operating system just executes the page fault handler, and then it returns to our code. Okay, but if the exception is not restartable, then it just terminates our code, like the divide by 0. So if the inter CPU divided by 0 is detected, then it terminates the execution of our binary, right? So it terminates the program and then it reports error. Okay? Then we need to debug. We need to debug our code, right? So that's why. So the compile. So actually the program language supports the debugger, right? Or actually called compiler. The compiler also has the debug options. Then actually it just includes some code for debugging. Okay. Okay. So as I mentioned, the exception works like the jump instruction. Okay. And then also it's very similar to the mispredicted branch instruction. Okay. So and then let's see how the exceptions are handled. So handled in CPU. So let us assume that the exception is detected for this add instruction in EX stage, right? So it's an add instruction, like, but so let us assume that the exception is detected in EX stage. Then what should we do? If the exception is detected, then it means this is the abnormal case. It's an abnormal case, which means actually we need to prevent the update of register or memory because it's abnormal case. Then if the exception is detected, but if the register is updated or the memory is updated, so what does that mean? Which means these data are updated by unexpected events or abnormal events, right? And then if the registers or memories are updated, it's very hard. It's very hard to restore to the normal condition. Okay. So firstly, we need to prevent X1. We need X1 from being updated. Okay. Also, if the exception is detected, then the exception handler will be called. Okay. And then if the exception is handled, then we need to return to this instruction. So what does that mean? And then in the pipeline architecture, there are many instructions, right? Many instructions are in the pipeline architecture, pipeline the CPU. And then we assume that the exception is detected in the EX stage. So it means we can distinguish instructions. So these instructions are previous instruction, and then these instructions are next instruction, right? And then if the exception is handled, we need to return to this instruction. Then what should we do? We need to complete the previous instructions. We need to complete. So if the exception is detected, the instructions in memory and write back stage needs to be completed because these are previous instructions. And then exception is not detected for these instructions. So these instructions need to be completed. How about the next instructions? The instructions in idle stage and instruction fetch stage. So these instructions are after this abnormal instruction, the instruction that causes exceptions. And then we will return to this instruction. So we need to flush, cancel these instructions. So next instructions needs to be flushed. Okay? Because we will return to this instruction again after the exception is handled. So and then the flush also this instruction. This add instruction also needs to be flushed because this instruction will be executed again after the exception handler, right? If the exception is kind of a restartable exceptions. Okay? So you need to understand this. If the exception is handled in a certain stage of the pipeline, then the previous instructions, these instructions need to be completed, and then these instructions, the next instructions, and then the current instructions need to be flushed. Okay, it needs to be cancelled. And then also the PC and then causes of exceptions need to be stored and then calls the handler. So this is the required operations for handling exceptions. Also, our homework also includes some questions regarding the exceptions. Okay, so you need to apply these rules to solve the homework questions. Okay, so this is the pipeline that handles the exceptions, but actually in this figure, actually this is added as COSE and SCPC, right? So actually it shows some required registers for handling exceptions, okay? And then actually we need to understand this one, okay? So actually, so I will explain how the exception is handled in the pipeline using this example. So in this example, these are PCs of the instructions, and then so these are instructions, and then let us assume that the exception is detected for this add instruction, and then this is the handler code, okay? The exception handler code, okay? So, and then as I mentioned, so let us assume that the exception is detected when the add instruction is in the EX stage. Okay, so in this case, these are previous instructions like OR and AND instruction, and then these are following instructions. Okay. So and then the exception is detected. And what will happen? So as I mentioned, we need to complete these instructions. So the previous instructions will not be flushed. Okay. And then the next instructions, the following instructions, and then current instructions will be flushed. And then the SCOSE and SCPC is updated, right? And calls the exception handler. Okay. So in the next cycle, you know, is clock 7. So you can find the bubble is here, bubble is here, the bubble is here. So what does that mean? It means the sub instruction and then this load instruction was flushed. Also, this add instruction was flushed. Okay, but you can find the OR instruction. OR instruction is the previous instruction, so OR instruction is in the right backstage. Okay, so which means the OR instruction will update the register file. Because OR is here. Then you can find the first instruction of the exception handler. Okay, because it jumped to the first instruction, the first code of the exception handler. Right? So you can find the ST here. So this is the how the exception is handled in the pipeline architecture. And then also we can also assume some cases sometimes the exception can be the multiple exceptions can be detected in the pipeline architecture. And then actually in the homework questions, I assume this case the multiple exceptions are detected, right? Then also you need to figure out how the instructions are handled based on this rule, okay? So and then this slide explains how exceptions are handled. But you can apply this rule to solve the problem. So what multiple exceptions, okay? Then how can you handle the multiple exceptions? Actually, you can apply the same rule. Actually, in order to solve the problem, actually that is the last question. That is the last question. And then in order to handle the multiple exceptions, but we can just apply the same rule. So in the pipeline architecture. But you need to remember that exceptions needs to be handled in the order of instruction. So needs to be handled in the order of instruction. What does that mean? Sometimes we can think that the exceptions need to be handled in the time order. Which means if the exceptions detected earlier can be handled earlier, but it's incorrect. So you need to remember that in a program, exceptions handled in the order of instructions. Okay, so this is called the precise exceptions. Okay, exceptions need to be handled in the order of instructions. So for example, so in the question, so in the homework question, I assume this multiple exception case, and then actually the exceptions is detected in the ID stage first by the following instruction, and then after that, the exception is detected in the memory stage. I assumed this case. So because the ID stage is here, actually, even though the instruction is the following instruction, then this exception can be detected earlier, right? But after that, the exception can be also detected in the memory stage, like the page fault. This exception can be detected later. In this case, this exception needs to be, what happened? This exception needs to be handled first, and then this exception needs to be handled later. Even though the exception is detected in the ID stage first by following instruction, but it needs to be handled later. Okay, so this is called the precise exceptions. Okay, but if you follow this rule, then actually the precise exception is automatically supported. Why? So based on the rule, so let us assume that this exception is detected earlier in the ID stage, but the instructions in EX memory and write back is preserved. It needs to be completed, right? And then only these instructions, the instruction in instruction fetch will be flushed. Okay. Then after that, the exception is detected in the memory stage. Then what will happen?
Then because of this exception, instructions in write back will be it's completed, but these previous instructions will be flushed, which means even though the exception caused by this instruction in the ith stage called the exception handler, but because of this exception, this handler code will be also flushed. Okay, and then it is preserved. So because the previous instruction is always preserved after the exception, then we can just handle exception in the order of instruction. Then this exception is called the precise exception. Okay, then sometimes the processor cannot support the precise exception. So because so as I mentioned, actually the modern CPUs, the pipelines of modern CPUs are very complex, and then sometimes the instructions are complete and out of order. Okay, then sometimes these CPUs cannot support the precise exception. But in the pipeline architecture can support the precise exception, and precise exception means that the exceptions handled in the order of instructions. Okay, so this concept is very actually important, right? So even though this is the rare case, our hardware needs to support the rare cases also. Okay? And sometimes the precise exception, actually all the CPUs cannot support the precise exceptions. And then sometimes this is called the imprecise exceptions. And then actually operating system handles the imprecise exceptions. Okay, but in the pipeline architecture automatically supports precise exceptions. Okay. Okay, so this is the end of this chapter. Okay, so the pipeline is very simple, but the detail is very complex. Okay, you need to understand this one. Okay, thank you for your attention. See you in the next class.